All right, some calculus warm-up. If you've been graphing functions using derivatives, this is where we're at. And the two on the left here are they even or odd or neither? And these are important facts, okay? Because if you know they're even, you only have to go from 0 out and then mirror it. And if you know they're odd, you only go 0 out, and then you know it reflects across the origin, right? So even and odd save you a lot of work. We know that an even function looks like this. For the opposite x value, you get the same y. And you know for an odd function, you get this. Now, I'm going to do them out of order. If you want to pause the video, I'm going to do number 2 first because this one's really easy. We think about putting negative x in here, and we recognize that an even power is going to keep it positive. So when you plug in negative x, you're obviously going to get the same function. So this one's even, and I'm not even going to waste time proving it. All right, if you want to put in negative x, fine. My guess is a lot of people are going to screw number 1 up. The answer is number 1's odd. And I think a lot of people are going to say neither. All right, number 1 is odd. And I'm going to just take the odd function up here, and we're going to prove it, okay? And I'm going to move this one down. All right. If you plug in negative x, into the function, you get x squared minus 1 over negative x cubed. Well, if you bring this negative from the bottom out front, is it negative f of x then? It is. A lot of times, number 1 gets to it because they're looking at the powers. If you're going to look at the powers of a rational function, all right, you really can't do it as a single thing. You really got to check it using the definition or make this step. I could show you why this is odd this way too. So you get x to the negative 1, x minus x to the negative 3. Now it looks odd. Do you guys agree? All right. So again, we like to substitute negative x, though, to be sure. Especially when we're doing exams or more complicated things. All right, even or odd, practice. Next thing we're going to do is graph this function, y equals x minus 3x to the third. All right, so let's go to a single page on this one. Does everybody see this as a line minus a cubic? If we think about our mother functions. All right, it's going to be that composite. So if I asked you the type of function, you would say it's composite, it's a polynomial minus a root. All right. Is it even or odd? If I plug in negative x, it is not going to be opposite signs. This is neither. All right, so it's not even or odd. I'll just erase it. I see that the domain of a line is all reals. The domain of a root function that's odd is all reals. So I immediately know that the function has a domain of all reals. And this is why we want to learn our mothers so well. And I see pretty quickly that I can also see that this goes through the origin pretty easily, right? If I plug it in 0. So I take the derivative, and I get y prime. I guess it was 2 things. Y prime is 1 minus x to the negative 2/3. And before I think too much and do some editing, I take the next derivative, which is y equals positive 2/3 x to the negative 5/3. I'm going to deal with the critical points first. Critical points occur when y prime equals 0 or is undefined. When I do this, then I get this. All right. I would move this over. I would cross multiply in my head. I get x to the 2/3 equals 1. So x is 1. So that's a 0, okay? The other thing I see is that this is undefined when x is 0. So there are 2 critical points. They occur at x equals 0 and x equals 1. And all this work is great, but for this situation, I don't need to see it anymore. So we'll do this and go x equals 0 and 1. Over here, y prime prime equals 0. Well, everybody, it's 1 over, it's 2 over 3x to the 5/3. It's just undefined at 0. You guys agree? So it doesn't equal 0 anywhere. Nope, just doesn't. And y prime prime is undefined at x equals 0. So my table gets pretty easy. It's 0 and 1 for x values. So I'm going to build my table in blue. X, F, F prime, F prime prime. The result, 0, 1. I would put, and I just put in that it goes through the origin here. I don't need to, right? But I'm just going to do it since it's there. And I know that at 0, this is undy and undy. Here I know 1 is 0. And everybody, I like 1 with this function. If I look up here, do you guys agree that putting 1 into the original function is really easy this time? It's 1 minus 3, it's negative 2. So I'll do that because my inkling is that we probably got something going on there. I got to check 3 regions for f prime. Okay, 3 regions. When I put in a really big negative number into the derivative, it's going to square it here, guys. So it's going to be, this will always be a positive term. So 1 minus a big number on the bottom, right? So if you're not sure, guys, use your calculator. You know what I mean? You can plug in 1 minus, you can actually plug it in your calculator. 1 minus negative 1,000 in parentheses raised to the negative 2/3, okay? And again, the number one thing is making sure you actually enter it right if you're not sure how it goes. And you can find out then that this number, you guys are picturing this, I hope, right? And I picture this, guys, that's the cube root of x squared, okay? If I plug a big number in there, that is going to make it 1 minus a fraction. So this is going to be positive. It's increasing, okay? Then between 0 and 1, all right, I think of half, all right? And again, over here, I'll tell you right away that I know it's got to be positive in here. Now, the only question is, what's it do at half, right? And again, so if I clear this. Here I find that in between it's negative. All right. So everybody, like a lot of composite functions, the outsides are pretty defined, you know, but the around the origin gets interesting. If I go to y prime prime, all right, you notice it's odd, right? 2/3 is positive. So to the left of 0 is negative. To the right of 0 is positive. Let's start right away with the easy thing here on f prime prime. It goes concave down to concave up. This is a point of inflection. Okay? And if I ask you to do the intervals, right, you would say negative infinity to 0 and 0 to infinity for these. All right? If I change colors here, we'll go blue or green. Here we see it's increasing, right? So it's increasing, and then it goes to decreasing, then it goes increasing. Okay, first derivative rule. It goes positive to negative. It goes positive to negative. Obviously, this has to be a local max by first derivative rule. Then it goes negative to positive. This is obviously a local min. If I asked you to do the intervals, right, you would still have to, you would have to sit here and do all this notation, right? Oh, not 2. 0 to 1. And then 1 to infinity. Those would be the intervals of where those happen. All right? And actually erase this, got a little mucky, right? A local, and It decreases from 0 to 1. All right. We now have all the ability to make a graph. All right. So if I go add a page, go dual page. I get my table in view. It goes through 0, 0. It goes through 1, negative 2. All right. It is concave down and increasing until 0. All right. The derivative is undefined, and it is then concave up. And it's 0 here. And then it goes, stays concave up and increases. Everyone, it looks something like this. It has a bird at 0. And it has, and that's what you said, Trent. Yes. You did say that. I'll put credit on YouTube that Trent Davis, Mr. Hansen, was wrong. We were talking different things, though. That you saw that it was a bird is impressive. It is a bird because the function, and let's be clear about this, guys. From the original function, you know it went through the origin. You had a pretty good idea it was going to be a bird because what did you know about the derivative? It was undefined. Good catch, Trent. My bad. Because I wasn't answering that question. But now here's the graph.
Yeah, it's so nice to be.
And it's continuous, so it has to be a bird. And we knew it was continuous at the very get-go because what kind of functions are the polynomial and the root function? They're both continuous. Again, and that's what set us to this thing. Now, everybody, let's be clear about this. This is a continuous function that has a non-differentiable point. Not every continuous function is differentiable. But what do we know about every differentiable function? If it has derivative everywhere, it is continuous everywhere. All right, good problem. This would be a complete fair one for a test because it has easy points to discover. Do you guys agree? The solving here is not a struggle. It's the calculus that you have to do it with, all right? Keep practicing.